Alright, so I apologize. One bad cable will apparently throw off your lecture for a whole hour. So I kind of threw off my plan for the week. So I was going to lecture hard today, and then Wednesday I was planning on playing around with some stuff. But I'll still get liquid nitrogen for us, and I'll probably still do some demos, but I did not do the demos how I wanted to do them, since I prefer that I would have captured them for our online audience, but with technical difficulties, that just didn't happen. All right, so other announcements. Check your grades, check your grades, check your grades. So I'm thinking that I'm pretty close to being caught up in this class. Maybe there's a few straggling assignments. I need to get people's bonuses in, but just make sure that you're checking your grades. All right, so this chapter is all about state changes, so solid, liquid, gases, and solubility. So let's just start from the top and see how far we get. And so this is just kind of a recap of solids, liquids, gases. And so we said, right, solids, they have to have a fixed shape and a fixed volume. So that was kind of the key point. And then we said a liquid, well, a liquid has a fixed volume. And so you might want to highlight that. But of course, right, we know our liquid takes the shape of any container. And then gases, we said those tend to expand. And we had a term for gases, so we said that gases are compressible. And so that's kind of the key thing of gases, so they can be compressed right all the way down to a liquid, like y'all have seen in liquid nitrogen, I'm sure. And then obviously, right, they can expand to fill this whole room. And so what is a gas? And so I like to think about water when we talk about gases, because we've probably seen water in all three states of matter. And so you know when water is a gas, of course, it has a lot of energy, right? Because you probably took it and you were heating up your stove and watching it boil. And so you know if it has a lot of energy in it, then, right, it's composed of particles that are moving really fast in their containers. And so, right, they're just moving around randomly. And so we kind of have to take some liberties with these gas laws, and we make a few assumptions. And so part of that is this kinetic molecular theory. And so they say that gas particles move in a straight line. And so we assume no intermolecular forces, so they're just moving in straight lines until they collide with our container or another particle. And then, of course, bounce off. And we assume that the collisions are elastic, aka, right, we're not accounting for any energy loss when they meet or anything, just assuming perfectly elastic collisions. And so then if we think about this, so what is a pressure? So molecular collisions are pressure. And so I always like to think about a balloon. And so this is, of course, my wonderful balloon picture. And then your balloon inside, so we have to think about, well, how does your balloon stay inflated? So it's kind of cool. And so your balloon has to work against the atmosphere. So, right, you have to think that the atmosphere is beating against your poor balloon. But, of course, your balloon is beating back. And so, again, you filled your balloon with air, and it can hold its shape since it has a bunch of collisions, right, on the inside of your balloon. So hitting the wall, keeping it inflated against our atmospheric pressure. And so if everything is really just these molecular collisions, then we can say that it's related to pressure. So we just need to define pressure. So pressure is the force exerted per unit area by gas molecules as they strike the surface around them. And so, of course, right, that force gets distributed by that area. And so if you make the container smaller, so of course that would increase your pressure since you would have less area. So that's one way to look at it. And so gas pressure is a result of the constant movement of the gas molecules, and of course, again, they're collisions, right? So again, you're thinking about them colliding with the inside of your balloon, or as we look at other things. So we'll look at kind of what tools are used to measure pressure, and it's again that beating down of those molecules actually colliding. And so, of course, we'll kind of see these factors, but as you have more gas particles, right, that's probably going to lead to increased collisions, so increased pressure. Your volume, so we'll see, again, thinking back to the area, so if your volume is larger, your pressure is going to go down as those collisions are spread over a larger surface area. And then, of course, we mentioned speed. So the higher we heat them, the more energy they have and the more collisions. And so like we mentioned, we have our kinetic theory of gases, where we said that collisions are elastic. And if there were to be an exchange of energy, this would be inelastic collisions, but that's just more of an aside. And so what units will we be seeing? And so we'll see ATM, and then if you notice, so millimeters of mercury and torr are used pretty interchangeably. And so again, they translate the same. So 760 millimeters of mercury is equal to 1 ATM. That's also 760 torr. And so notice how the pressure is measured. So this is a bunch of mercury, and then we have a glass tube that's vacuumed out. And so right, you have the pressure, so all those little molecules are smacking down on the surface of the mercury, and so that pressure pushes the mercury up the tube, and so that's where that 760 millimeters comes from. And so you might also see this inches, so of course that's just converted from millimeters to inches, so you'll see that as well. And you mainly want to be an ATM for our calculations, but I'll point out when it's necessary. And then we have other just units to be aware of. So we have pascals and kilopascals are used. PSI, you might see this on your car. So like a typical tire is around 33 PSI or so. And then we mentioned torr, millimeters of mercury. And then so if you look at like a weather station, they tend to report it in bar, and so bar is really close to ATM, but you might see that, so that's also relevant. Again, ATM, this is kind of like our standard unit. So I'll put standard chem unit. And so then there's 4 basic properties of a gas, so how we can characterize it. So we can say what pressure the gas is at, how much volume it's occupying, the temperature, and then the temperature is always going to be in Kelvin. So if you need to star this, I would. And then of course we'll also express the quantity in moles. And so all of these properties are interrelated, so you'll have a lot of fun with this on the homework. And you'll kind of see if you change one law, then the other ones are changed. And so then we'll kind of look at these simple gas laws. But again, right, my goal is not for you to memorize all these things, and I don't really care if you know what the names are, but we just want to be able to kind of derive these simple laws from our ideal gas laws, but we'll get there. And so let's start with Boyle's law. And so this started when they were testing, so these little J tubes are just sealed tubes of either gas or whatever substance they're looking at. And so then they measured the volume of different samples of gas at different pressures. And so they started to kind of notice this thing. And if we look at this, we have our piston here. So our volume is at 1 liter. And so if we half our volume then, so notice half the volume causes a 2 times increase in pressure. And so then we're given this relationship. So as volume decreases, pressure increases. And so it says it's directly proportional to inverse pressure. And so what kind of happens here? Why do you get kind of a stall out? What do you imagine? So what's the problem as we get to these extreme temperatures? And so we have to think, right, at these extremes of high pressure, eventually we get to a physical limitation. So the atoms itself, right, they still have to occupy some space, so we can't just squash them down to infinity. So yes, at some point, right, the physical size of atoms matters. So they do take up space. So there's kind of our limitation. And so again, we said that the pressure is inversely proportional to the volume. So again, as volume decreases, pressure increases. And so we get this formula. And so yes, you could go ahead and scramble and copy it down. But again, I want to show you all these, and then we'll kind of go back and rederive them from their ideal gas law. And so some relevance with this is, of course, with diving. Has anybody ever dived? We had somebody in my summer class. I taught oceanography, and we were talking about diving. And some guy, I guess, had experience diving, but also saw some other guy freak out. And well, we'll talk about what happens. And so let's look at what this little scenario says. And so for every 1 meter of depth, a diver experiences approximately 1 additional atmosphere of pressure. And so this is pretty fascinating. And not to go like too on an aside, since we already had tangent the class today, but you can kind of at least think about that Titan vessel, right? It was the Titan that exploded, right? And so part of, again, I don't want to go into like the engineering of that Titan ship, but you have to imagine it has to be engineered really well. So ideally, you want kind of a spear design. At least that's how a lot of the deep sea diving vessels are created. Because of course, the problem when you dive deep is you have to have your air, and you have the threat of this, right, collapsing, of course, like what happened under the incredible pressure. And so again, we won't go into the design. So you want a nice design that can take that pressure. Obviously, the material composition comes into play. So I think that was part of the issue with that vessel. All right, but what do we care about? So it says at 20 meters, for instance, the diver experiences 3 atmospheres of pressure. And so again, we can look at this, and so we can see, so what happens to our air volume. So our pressure is decreasing by a factor of 3. So this is why you wouldn't want to quickly rise. So right now it's saying if we're at our depth, why don't we want to rise quickly? So have you heard of that with divers, that you want to go up slow? And so you have to think about all the gases that are dissolved, right? They're in your blood and everywhere in your lungs, so floating around. And so if you go up too quickly, or you don't allow yourself enough time to rise, right? So then the gases, so it says, right, your volume is going to expand by a factor of 3. So think about, right, all the gases in your bloodstream, they're rapidly expanding. And so if you don't rise properly, and it also says, right, exhale, so you want to be exhaling to get rid of that, all those gases, right, coming out of solution. So if you don't do that, you could potentially damage like your internal organs or have like blood vessels pop. And so I think the horror story that my former student was kind of sharing is that he knew a person who was like diving, and then they didn't give himself enough time to rise up, so they're kind of like panicking already. And obviously, right, you don't want to panic when you scuba dive, because then you're breathing in even more air. But I guess he had to rise kind of quickly, and then that started causing him to have like issues. I think like blood vessels were breaking because he was having like vision issues, and so he did have to go to the hospital. But that's just showing you, right, why it's important to be careful, why we have all these protocols. So that's why they make you go slowly. And of course you need all this training, because stuff can happen, right? And you don't want to panic and then rise too quickly and not follow your protocols. And that's also why they have all those rules, like only use half a tank and monitor your air all the time. So all that comes into play.
When you free dive, is it because you just take in one breath that like you can rise however fast you want?
Yeah, plus you can only go probably so deep when you free dive.
But there are people who like go really, really deep when they free dive, right?
I would have
And
to
they come
see.
back up just as fast.
Yeah.
Is it just because they take one breath? Or?
It's probably just because they're also like not going so deep. Because I assume when you go scuba diving, you go a lot deeper.
Yeah,
but
I mean like the world record though is like pretty deep for a free dive. I think it's pretty crazy.
Now I'll have to look into that, but yeah.
It's weird, yeah.
All right, let's try this practice problem. And so I'll give you the formula. So P1 V1 equals P2 V2. So as we breathe, we inhale by increasing our lung volume. And so if you're in the biology track, you can think about that, right? So your diaphragm literally goes lower, right? Makes you have a larger volume. And so that allows the air to come in. And so let's just say a woman has an initial lung volume of 2.75 liters, which is filled at atmospheric 1.02 atm. And so let's just say, right, this is right before the air rushes in, so your diaphragm has increased your lung volume to 3.25 liters. So what is the pressure? So I'll give you guys a minute or so to look at that. Bless you. So as you finished that, you had me really curious. So I looked at this guy who's supposed to be like one of the free diving record holders. And so I don't know, these people just like physically train so that their bodies become better at handling the decompression sickness? Because I mean, that's really interesting. But if you look at this page, so it mentions that in this dive, he did have symptoms of this decompression sickness. And so, of course, what can also happen is if you have too much nitrogen coming out, then, right, in this case, he basically had too much nitrogen and almost fell asleep. So that's kind of crazy, right? So you can think about that's if you inhale, right, a bunch of non-oxygen gas, then your body like starts shutting down and goes to sleep. And then it also mentions, so this is kind of interesting. So they must have, right, oxygen available for these people. But he mentions, right, he felt weaker. And then if you keep reading, so he did suffer some strokes due to decompression sickness. So probably, right, like minor strokes. So thinking about, right, blood vessels, even small ones just popping. So I'm assuming that that's kind of what happened. But yeah, that's kind of interesting. Like, I don't have a good explanation as to how people can do that or like what they do to, but obviously it does cause issues. But I mean, yeah, it's pretty. I'd be curious what kind of training they do. All right, do we have an answer? So our setup should look something like this. So we have our initial conditions and our final conditions. And so in this case, let's just talk about our units real quick. So this is just a relationship. So units don't matter too much as long as they're all the same. So right, we're in liters, that's cool. We're in ATM, our answer will be in ATM. This could have been in torr, in milliliters, as long as it's the same. So that's fine. And so then we're solving for X. And so what did people get when they plugged it in? I can pull up my calculator. Someone give me the answer. So did we get 0.86? So I see a lot of nods. And my calculator's off the screen. So 0.863, or yeah, 863 ATM. Questions about that one? All right, so now let's look at Charles's law. And again, I don't really care that you know that this is Charles's law, but let's just look at, so what is this volume temperature relationship? And so now we have the volume of a fixed gas at a constant pressure increases with increasing temperature. And so that kind of makes sense, right? So if we increase our temperature and we want everything else to stay the same, our volume is going to have to increase. And so let's look at some other thing. Have you guys done these PhET simulations before in your classes? So I kind of figured you had, so I'll post a link just in case. But you can play with this at home, so this would be a good thing to play with, especially since we started lecture super late. And so let's, how do I do this? Hold constant, I don't want to hold constant volume. There we go. So now I want to hold pressure constant. And so this is just saying right, if we heat it up, so now I'm going to heat, and of course, as we heat, we can just see our container is expanding to keep up with our 7 atm of pressure. And so that gives us this equation here. So we have our initial volume over our initial temperature equals our new volume over our new temperature. And so what's important here is that it's really important that we use Kelvin. And so this is because this has thermodynamic relevance, but what that means for y'all is like we can't have a negative temperature or else it doesn't make sense. And so with that, we just want to be in kelvins. And so I'll put that, so no negative temperatures. And so again, always, always, always use Kelvin. So I can't emphasize that enough. If there's one mistake that students will do, it's putting your temperature in Celsius. So as long as you're in Kelvin, you're in really good shape for these problems. And so a lot of this is also related to its kinetic energy. And so again, if we increase our temperature, then that increases our average speed, which is of course related to our average kinetic energy of our particles. And so again, like we saw, as we heated it up, the volume expanded so that our pressure is unchanged. And so this is kind of cool too. And so right, if we could just extrapolate all these lines of these substances to 0, then they would make a nice linear line. But of course, we have the issue is that gases do eventually condense into liquids. And again, we'll look at these intermolecular forces that do drive that. And so again, that's a key point just to note when we're talking about these gases, that we're just talking about ideal gases. And again, that's why our true gases condense, so we're ignoring intermolecular forces right now, but we will talk about them later. So Wednesday we'll do a little demo of this that kind of shows us better. And so again, we're just looking at when our temperature of our gas increases, our particles move faster, and we have greater collisions, more collisions. And so we could see this, again, I'll demonstrate this on Wednesday. So we'll put a balloon in some liquid nitrogen and we'll watch it kind of shrink. And then of course we'll take it out and it will expand. But we'll save that for Wednesday. All right, let's try this practice problem. And I'll give you the formula again. So V1 over T1 is equal V2 over T2. So we have some gas at a volume of 2.8 liters is at an unknown temperature. And then we submerge the sample in ice water. So again, make sure you convert to Kelvin, and its volume decreases to 2.57 liters. So what was the initial temperature? So I'll give everyone a minute or so to work on that. we still plugging away at this? Okay, I'll give people more time. So let's hear what we got. So let's see. So we had an initial volume. And so, right, help yourself label these. So we have volume initial. We don't have a T1, but then we have T2 and V2. So then we can plug everything in. So 2.08 liters is equal to X over 2.57. And then what was our temperature then in Kelvin? So 273, I like the 0.15. And so then now we just need to multiply and divide. So 2.8 times our temperature. And of course divide by 2.57. So did we get an initial temperature of 297? So our K 297 for initial temperature. And so then let's subtract. So minus 273.15 if we're feeling really precise. And we should get about 24 degrees or so in Celsius. Questions about that one? And so now if we look at the next one, so this is kind of, I feel like it's self-explanatory. And so volume and moles have a direct relationship. So what does this mean? And so again, if we hold pressure and temperature constant, then as our number of moles increases, then our gas must increase. And again, that makes sense. And so this is also kind of cool. This will come back later. But so equal volumes of gases contain equal numbers of molecules. So again, the identity of the gas does not matter. And so again, we have this relationship. So V1 over N1 is equal to V2 over N2. And so again, right, this makes sense. So of course, if we have more molecules, then obviously we're going to have more collisions hitting the wall. And so of course, if we want to keep pressure constant, volume must increase. So let's try this one. And so I'll rewrite our formula again. So V1 N1 equals V2 N2. And so now we have a male athlete has an initial lung volume of 6.15 liters during a deep inhalation, and it contains 0.254 moles. And so it says his lung volume decreased to 2.55 liters, and then just watch what the question's asking. So it says, how many moles of gas does the athlete exhale? So I'll give you guys a few minutes to work on that. Let's see, do we have answers for this one, or? So let's see what y'all are thinking. So he said he has an initial lung volume of 6.15 liters, and it was 0.254 moles. And then it said, well, went to 2.55 liters. Except what are you solving for with X? So moles, but that's moles in the lung still, right? So then once we get this, we'll have to subtract. And so what did y'all get for X?
0.105.
So is that what other people got? 0.105? So I think I saw some nods. So let me just put this on my calculator. So 0.105, just like you said. So moles in lung. But the question asks, how many did we exhale? So now we have to subtract, so 2, or 0.254 minus our 0.105. And so then we should get 0.149 moles exhaled. Excellent. Any questions on that one? Yeah. So did you have this on the setup? And then, so then we just do our cross multiplication, so 0.254 times 2.55, and then divided by 6.15, so just double check calculator errors and all that. And so again, that's why it's always good to, on an exam, show your proper setup, so if you typo stuff, I can figure out what went wrong. Just a calculator error or something. All right, we have 10 more minutes, so I think we'll at least get to talk about our ideal gas law. And so let's look at this ideal gas law. So now we're saying, well, we can summarize everything we just learned into one equation. So we have PV equals nRT. And so now let's kind of go through, so they have a derivation there, but let's go through the derivation. And so, right, all you need is PV equals nRT. So if we start from here, we can derive all the other gas laws. And so let's kind of go through this. Well, what the heck is PV equals nRT? So, right, P, that's just pressure. And so in this ideal gas form, it's going to be an ATM. So volume is, again, going to be in liters now. N is still moles. Now let's talk about R. And so R is 0.0821, but let's talk about that. Sorry?
What is moles?
Oh, I said let's,
Or can you just go by hand?
oh, sorry.
No, you're good.
So yeah, N is moles. So it's still, so pressure, volume, moles, but I wanted to look at this constant because let's just say you just search gas constant. And so if you look at gas constant in Wikipedia, right, it gives you this jumble mess, but pay attention to the units, right? So the units tell you which one we're using. So not to confuse everybody, but right, we're liters, ATM, Kelvin, moles. So this is the units that we're working in. And oh, yes, that's our gas constant that we set in our notes, 0.0821. So obviously it's rounded here. But I just wanted to point that out. So right, that's why I'm saying use these units, use this gas constant, because if you don't, right, then it means you probably need to be using another one. So that's where that came from. So again, this 0.0821 is for our liters, ATM, right, Kelvin, moles, unit. And then temperature is again Kelvin. So our 0.0821, aka this is just a constant. And so PV equals N, and of course T, we said was Kelvin. And so now let's figure out, well, how do I derive all those other formulas, right? Our Avogadro's law and all the other stuff. And so let's rearrange this. So we could do PV over NT is equal to R, right? Because R is just a constant. And so now I could set, well, if PV over NT is always equal to R, then I can have P1 V1 over N1 T1 is equal to R, which is also equal to P2 V2 over N2 T2. And so of course now we can just get rid of this R, and you have this P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so this is my other favorite form of the gas laws. And so you can start to see, well, this is how we derive them all back out. And so now I'll skip down to the lecture notes where they show this. But right, we get our Boyle's law relationship. So you can see if we hold n constant, and so any variable that's constant just goes away. So if moles is the same, they cancel out. Temperature is the same, they cancel out. And so you're left with P1 V1 equals P2 V2. Then we can get the other ones back out, right? Volume and temperature, or moles and volume. So all those are all there. It's just you cancel out whatever variable is constant. So I'll put that in as a note. So variables that are constant cancel out. But this is the best form of it. So not sure if it comes up in your homework. We can do maybe some more examples on Wednesday. But if you're unsure what to do, but you have all these final and initial conditions, this would be a good form of the equation. Or if you're just given, right, one pressure, one volume, moles, temperature, then you might have to use this form. But these are the two most useful forms, and then you can just derive everything from them. And so blah, blah, blah. So this just goes through that same derivation. So just showing you why that works. So last problem, and then I'll let you guys skedaddle. So calculate your volume occupied by 0.845 moles of nitrogen gas at 1.37 atm and a temperature of 315 Kelvin. And so R 0.0821. So let's look at this one. So we have, right, PV equals nRT. And so I wanted to go with this one. And again, I'll just kind of write this one down here. But we can tell, right, this one is not appropriate. So we don't have enough information, right, to make use of any of this. There's no before and after. And so that's always the key. And really the key in figuring out what to plug in anyways. So we have moles, we have ATM, we have temperature, and you could always write that to the side. But it looks like it goes best into here, and we're trying to calculate volume. And again, we have R, that's just a constant. And so let's plug that in, and again, everything's in the right units, so pressure is in ATM like it needs to be. Our volume's going to be in liters once we get it out. And again, that's all based on your gas constant. And UC, so luckily they already gave it to us in Kelvin. We don't even have to think about it. And so now I'll just punch everything in. So I'm just going to solve for the side without variables first. So just multiply everything. And then I'm going to divide by my pressure so I can isolate my volume. And so did we get 15.95 liters? Excellent. I see lots of nods for that. And let's see, proper would be 3 sig figs, so I think it ends up rounding to 16.0 liters, but again, as long as you're somewhere around there, that looks pretty good. All right, we'll stop there, and then Wednesday we'll pick it back up and probably do some more demos. And we might have to push this on to next week as well with lecture, so we'll see what happens.